Okay, here we are. We are looking at, good evening everyone. We are looking at Biconditionals and Definitions, page 101. Problem set is 2 through 28. So this is how this works. Now hopefully you have watched or have a fair understanding of how conditionals work. And if not, go back, watch that conditionals video. But here we are talking about biconditionals. And we all know what bi means. Bi means two. We have bicycles, biannual, things like that. All that is two. Okay, so biconditional means two conditions. Now this happens when both, and again, if you don't understand any of the terminology I'm using, go back, watch the other videos, come back, pick up where you left off. We have these two conditionals. Now what we're really looking for is whether or not a conditional is reversible. Much like some of my bow ties, can wear them both ways. The conditional is reversible if my kids are making fun of me, and that's okay. If this is true and this is true. So if we have a conditional, if P then Q, and that's true, and then we have our converse, which is if Q then P, and that's true as well, then they are reversible. It doesn't matter which way we say it. So let's look. I'm going to do some evens here. I don't want to take away any of the fun. I want you guys to be able to work this whole problem set all by yourself. It's only 14 problems. Hate to deprive you of even one of them. So let's look at some odds. So we go, let's start with number 7. And we're going to go our hypothesis. If two segments have the same length, then they are congruent. Okay, so we look at that and we go, is that true? And we go, yes, that's true, mainly because the problem set says each conditional below is true. So that's easy. So we know that that's going to be true. So now what we want to do is we want to write our converse. Now remember, the converse is what happens when we flip the conditional and the hypothesis. Okay, so we go, if two segments are congruent, then they have the same lengths. We go, is that true? Well, yes, it's kind of the definition of congruency. Two things having the same length or measure. Remember, congruency happens when we are looking at the same lengths. Equality happens when we are looking at the same number. Okay? So these are both true. So now we have to look at a biconditional. Okay, so we're going to write two of these two conditionals in the same exact statement. Now, before we get there, there's a term that you have to become familiar with, and that's that. IFF. It is pronounced if. Okay? Or just if. And what that means is if and only if. Now this term right here, if and only if, or IFF, is the hallmark of a biconditional. All biconditionals have them. And what that means is it doesn't matter which way we write it, both are equally true. So this is what we would do. We take our first statement, we're going to take our hypothesis there, and we're going to go and we're going to drop the if. We're not using an if-then statement. Okay, we go 2 segments have the same length. Okay, so we look back here and we go, oh, hey, 2 segments have the same length. And then we're going to use this puppy right here, if and only if. If and only if. Then we go back, look at our second statement. They are congruent. Okay? And that is a true biconditional, because it doesn't matter which way you read it. 2 segments have the same length if and only if they are congruent. Flip it around. 2 segments are congruent if and only if they have the same length. Both are equally true. So we want to be able to look at that and go, okay, that is true. Both ways it's true. It doesn't matter. So that is what is called a good definition. A good definition is one which can be stated as a biconditional. If you look back in your notes and look when you actually wrote down the definition of congruent, you'll see that it's kind of the way that we talk about shapes and lengths and stuff like that in geometry. So numbers are equal to each other, triangles are congruent to each other. And that's it. So let's look at number 9. Okay, I'm going to look at number 9 because it's a little bit different. We're just going to do 3 on this one, and you guys should have it. So number 9. If a number is divisible by 20, then it is even. Okay, so let's think. Of all the numbers divisible by 20, are any of them odd? The answer is no. 20 is even, so 20 times anything else is going to be even. Any even number times an even number is even. Even number times an odd number is even. So 20 times anything is going to be even. So that's true. So now what we're going to do is we're going to flip it around and write the converse. We also know it's true because it says that each conditional is true. So we go, if a number is even, and then we write our previous hypothesis, our P. Remember, this is P. If P, then Q. That's our conditional. Our converse is if Q, then P. So now we write our hypothesis from the first one. If a number is even, then it is divisible by 20. We look at that and we go, no, that is false. It's false, and since it's false, we need to give a counter example. And I'm going to go super simple. It's false because of the number 10, or 18 is the closest one to it. So we know that 10 is even. So we look here, and if we were to look kind of like the Venn diagram here, we'd say all the even numbers right here. Right? That's our Q, sorry. And then we go, do all of those numbers fit in here? So we say, if a number is even, then it has to be divisible by 20, and that's false. And so that's not a good definition of even. Okay? Because it can't be written as it's not reversible, and therefore can't be written as a true biconditional. Hope that made sense. Moving on. We're going to look at number, let's go 17. 17 states, an angle is a right angle if and only if it measures 90 degrees. Now, what you're being asked to do here is write the two statements that form each biconditional. Okay, so there are two ways to go around this. I'm going to do both of them so you guys kind of understand the full implications of it. The first is super simple. You just want to write your P and your Q. Just so you know, we didn't go over this, but the symbol for a biconditional is that. So it's P, Q, and the arrow goes both ways. Again, we're talking about a biconditional, so we have two conditions. So what we want to do now here, though, is we want to write our P and write our Q. We look back here, we go, an angle is a right angle. That's our first statement. So we go, an angle is a right angle. And then we look back and we see that if and only if, and it measures 90 degrees. So our second statement, an angle measures 90 degrees. And that's it. The other way to do this is to write it as a true if-then statement. So we'd write if an angle is a right angle, then we'd probably put it measures 90 degrees. That'd be one statement, and then we'd write the converse of that as the other. If an angle measures 90 degrees, then it is a right angle. And those would be the two statements that if an angle measures 90 degrees, then it is a right angle. So that'd be the more comprehensive way to do it, because when we are talking about a biconditional, so we do kind of need those two true statements. We need the true conditional and then the true converse. And that's it. You have through 28. Yeah, I think we've kind of gone over everything. So again, any questions, tag them in the bottom, or ask me in class, or come in before school, after school, or at lunch. A lot of times I may not be there, and that's okay. Ask me. Let me know ahead of time if you're going to be there. I'll make sure I'm there. If you're going to be coming in before school, just let me know the day before. Say, hey, Mr. Renard, I'd like to come in before school. Plan on, I normally show up around 8:10. If I don't know anyone's coming, I might show up around 8:15, 8:20. If I know someone's coming, I'll make sure I get there. So that's it. We're up to date on this. Again, any questions, please, please, please let me know. I don't know what you don't know unless you tell me. And have a wonderful evening, everybody. I will see you in class.